Hello everyone. In this session, we will perform the binding free energy calculation of a protein ligand complex system using the GMX MMGBSA module after completing molecular dynamic simulation. Right. So yeah, I am in the current working directory. Like in the previous session, we have performed the molecular dynamic simulation of a protein ligand complex system of MDM2 and Na2D system using GROMACS software, right? So as you know, we have already carried out the MD simulation of or protein ligand complex system. Now we will move forward to analyze the real-time binding free energy calculation of the protein ligand system, right? So one of the most widely used approaches for this purpose is the MMGBSA and MMPBSA method. So in this session we will mainly focus on MMGBSA method, right? So and MMPBSA method we will perform after this session, right? So yeah, MMGBSA generally stands for molecular mechanics generalized board surface area, right? So MMGBSA is generally a computational technique that allow us to estimate the binding free energy between molecules like macromolecules, right? Any of the macromolecules like protein DNA, protein ligand system, polymeric system, right? So this method generally allows to estimate the binding free energy, the real-time binding free energy between molecular systems, most commonly between a protein and ligand system. We are in this session we will follow, right? So this method is particularly valuable in computer aided drug discovery, right? So as it provides insights into how strongly a ligand interacts with the protein system, and that is the molecular target, right? After the dynamics of the system are taken into account, like we have performed the MD simulation, the whole MD run, right? And what the consequences of the MD simulation of protein ligand. So this generally compared to the traditional docking score, MMGBSA offers a more realistic and accurate estimation because it incorporates structural flexibility and solvent effects observed during the MD simulation, right? So yeah, in this session we will go step by step to set up and run the MMGBSA calculation, and finally interpret the results to evaluate the binding affinity of our complex system, right? So yeah, I am in the current working directory, right? So just we need some input files, right? And we have already all the input files, like we need md.xtc, GROMACS file, tbr file, and index file, right? And most important is what the parameters files we have, like what parameters we are using, how much frames, how many frames we consider for the calculation, right? So we generally consider for this MMGBSA calculation is 1 to 1000 frames for this GBSA calculation, right? It's just the demo, that's why we are considering the small system, and very less frame, like 1 to 1000 frames, right? And if we want to publish the data in journals, right? So we have to analyze and we have to run the MMGBSA with the entire trajectory, right? Like we have performed the MD simulation for 200 nanosecond, 500 nanosecond, 1000 nanosecond, right? So like that we have to run also the MMGBSA on same trajectory of the 500 nanosecond molecular dynamic simulation trajectories, right? So yeah, just like this. We have the system, and just go for activation of or MMPBSA module, right? GMX MMPBSA module. So we have to activate it via using conda activate GMX MMPBSA, right? So we have activated the environment, right? And we have to write a command that leads to the real-time calculation of MMGBSA and MMPBSA, right? The MMGBSA and MMPBSA is the different thing, right? In this session we only perform the MMGBSA. After that we will go for the next MMPBSA analysis, right? So for the GBSA calculation, we have to write a command that is that the GMX MMPBSA minus I, that this is the input flag, right? GBSA dot in minus CS MD dot TPR minus CI index dot NDX minus CG 1 and 13 minus CT MD dot XTC and minus CP topol dot top, right? So this is the command, right? This are the input flags, right? This is the input flag, this is the file. This file contain the information about the parameters, like how much frames, how many frames we are considering for the calculation, right? What is the method, GBSA or PBSA, right? What kind of calculation, other calculation we want to consider in this calculation, like per residue decomposition we want, or binding affinity, and all the major calculations we need. So I have put all the parameters in this gbsa.in file, right? And yeah, the minus cs md.tpr, this is also the input file, minus ci index.ndx, right? This file contains the different groups of our molecular system, right? The protein, c alpha, and the backbone, and the ligand system, right? So 1 is represented for the protein, and 13 is represented for ligand, right? Because we want the binding energy between protein and ligand, so that's why we have given the 1 and 13. 1 is for protein and 13 is for ligand, right? And this is also the input flag, minus ct, that is represented for trajectory file, right? And minus cp is for the topology file. So just go for the hit the enter and make it run. Okay, so it will take some time, right? So yeah, it is started, right? And it will take 1 minute, I think 1 to 2 minutes for the complete MMGBSA calculation, right? You can see there's the parameters, all the environments and inputs, and force fields these are using, because this calculation is totally biophysics based. So yeah, there is the 92 residues, okay, in the protein, and this is the ligand, right? So yeah, it will use one CPU for the GBSA calculation, right? So just wait for some time. Yeah, the complex calculation is completed, right? The protein ligand complex is calculation is completed, and it is now calculating for the receptor, the protein, right? And it will calculate next for the ligand system, and after that combinedly it will give us the data of binding free energy and per residue decomposition. Yeah, yeah, the calculation is completed, and we can also analyze from the GMX module, give us some, if our system is graphics based, so we can visualize it in a real time system, right? So there's the option, we can see enthalpy minus TDS, binding, decomposition, right? So we will go for the binding, and yeah, this is the binding of our system. Yeah, it's around minus 35 or 36 something, right? We will see it. Okay, this is the delta G binding, okay, we are looking for, and the decomposition is yeah, there is the interaction diagram, which amino acid is more interacted with our ligand molecule, right? There's the valine 93, leucine 54, methionine 62, right, with the energy. And this is the energy diagram of our protein ligand complex system, right? The same energy diagram is just the describing how many frames we have considering, like we have used 500 frames, right? So yeah, which amino acid is more interacted with better energy, right? So valine 93 and leucine 54, methionine 62 is more minimized, energy minimized, right? So yeah, we can also visualize the real-time data in our files. Yeah, these are all the files are generated after the GBSA calculation, right? From this to this, and there's the two files, the main files. There's the data is stored of our GBSA calculation, right? So we can visualize it. Result data. Yeah, yeah. There's the thing. There's the minus delta G binding, and this is minus 36.23, standard deviation 2.44, right? This is the delta G binding minus 36.23, and this is the real time binding, right? So yeah, there is some other uh, properties and parameters that calculated, right? Like minus t days, gas, solvation. There is many thing, right? But the or targeted and desired thing is that the delta G binding, the real time binding free energy. This is the real time binding free energy of our protein ligand complex system, minus 36.23, and it is very good, and it is nicely contributed the MD simulation of our protein ligand complex, right? So yeah, this is all about the MMGBSA and MMGBSA calculation, right? So in the next session we will perform the MMPBSA analysis, right? So thank you, bye bye.